So, welcome to this lecture. Last class what we did, if you recall, that we went from the integral formulation to the differential formulation and we did it for the continuity equation just to show that how it actually reduces to the most common form that you are familiar with, like the divergence of velocity is equal to 0 for incompressible flow. For steady state compressible flow it is a little different. Okay. Now, let us take a look at the momentum equation. So, I am not going to go into the details of the momentum equation. What we can do is that we can apply similarly the divergence theorem. Okay. And we can show that this is the final form of the momentum equation, right. Now, here we have just done two things. The momentum equation, if you look at it, this is still the material derivative of the velocity, like we explained the material derivative in the last lecture. Okay. So, this is basically nothing but the convective acceleration. Okay. This is the body force term that we already know. Okay. This is the pressure, and this is basically nothing but the shear stress term. Now, this you did not see earlier because we only defined something called tau prime k relative, right. So, that we said was the total stress, if you recall, right. So, this total stress is nothing but a combination of the pressure, okay, that is an identity, and the corresponding shear stress component, right. So, the shear stress component is given by this expression. Okay. So, you can show, so this is nothing but the shear or the shear and the normal stresses, okay, and this is the pressure. Okay. So, when the body force is gravity, this xk becomes g. Okay. So, this is the most familiar thing that you are that you have seen. So, nothing but the convective derivative of the velocity is equal to the weight or the gravity term, the Laplace of the pressure and the corresponding shear stress term. If mu k is constant, okay, then this term actually becomes okay. So, sorry, this is not the Laplace, this is the corresponding Laplace of the velocity, that is the grad of the pressure field. Okay. So, the pressure is the grad of the pressure field, here it is the Laplace if mu k is constant. So, mu k you can actually take it out, got it. So, this is very simple, this is the corresponding Navier-Stokes equation that you are familiar with, right. Okay. Similarly, let us take a look at the energy equation now. So, the energy equation is something like this. If we apply the similar divergence theorem, okay. So, once again what terms we have the corresponding conduction term, the heat generation term, okay, and the corresponding work that is done by the body forces and the work that is done by the shear or the total stress, right. This, if you remove the mechanical energy terms from this energy equation, that means you just take a dot product with the momentum equation, a velocity dot product with the momentum equation and subtract it out, because we are not interested in the kinetic energy component that much, right. So, you can end up with this particular expression, okay, where this looks exactly similar to this, all the terms are still the same, okay, except that if you look at the right hand side, this is nothing but once again the convection. So, always the convection, okay. So, now the convection advection, whatever you call it. So, that is the left hand side of the expression. The right hand side term, however, if you look at each and every term, one is the heat transfer by conduction or diffusion mechanism. Once again, this is the total energy, that is actually internal energy generation. In many cases it can be actually equal to 0, and then the reversible rate of internal energy increase by compression, that is given by the pressure term. Okay. So, if the divergence is equal to 0, this term will also be equal to 0. Okay. So, it is like the work that is done by the pressure, essentially by compression. Okay. And the last term is basically nothing but, this particular term is nothing but something called viscous dissipation. In many cases this will be also equal to 0, but viscous dissipation is an important quantity that you may or may not have encountered so far. It is basically, so take an example like this, and this is an experiment that you should not do, okay, but this is just a thought experiment. Okay. Say if you have your fingers, if you can just look at my fingers. So, let us take a like a air hose. Okay. So, and let us put that airflow through these two fingers, okay, like this. Okay. You will not feel anything on your fingers, right. You might feel a little bit of a tingling and along the edges, but nothing bad happens. Okay. If the fingers are far apart and if the pipe diameter is small enough, you do not feel many things. Okay. But if I make the finger sufficiently close like this, okay, and I take a hose pipe and I try to purge the flow through that gap between these two fingers, okay, you will feel the burn. Okay. You will immediately your region over here is going to be burnt. Okay. Why is that burn that is happening? That is happening because of this viscous dissipation. So, why viscous dissipation is important? This is basically the work done by the shear stress, correct. So, the work done by the shear stress is a lot higher, okay, when these two fingers, which basically represent, say if you think in the analogy of two parallel plates, these two fingers are like two parallel plates. So, naturally the heat that is generated when the flow goes through these fingers, these two fingers of mine, it actually generates a lot of heat. But when I spread the fingers out, okay, the shear stress is very low. Okay. So, the viscous dissipation is important, especially if you have a very high velocity flow going through a constrained space. Okay. So, it is a function of the shear stress, and the shear stress, what it is a function we just saw in this particular thing, it is just basically the derivative, right, of the velocity, right. So, how do you write it? If you something like this, correct. Okay. So, if you look at it is like a typical component. So, this is basically the change of velocity with some distance, right. So, if this distance is very small and the change of velocity is high, you can generate a lot of shear. If you generate a lot of shear, your viscous dissipation can be a lot higher as well, right. So, the work done by viscous dissipation can be high. So, this can become a formidable component as the example that I showed you with my finger, but do not try to do this experiment, you will actually burn your finger. Okay. Okay. So, the essentially then the entire equation boils down to this particular form. This is the differential form, all the terms we have explained earlier. Viscous dissipation, if you can write it in a Cartesian coordinate system, right, cylindrical it will be a little different. You can see it is basically, these are basically, this is the normal stress, this is the shear stress, these are the shear stress in XYZ plane. You all know these are the basically the shears, right, okay, and these are the basically the normal stress components, right. Okay. So, this is the total expression that you have. Now, if you look at this particular expression, tau, say for example, let us take tau xy. Now, tau xy is what at per Newton's law, something like this, right, okay, the constitutive relationship that you all know, right. So, now when it is, this is basically UK because that is how we are writing it. If you look at this term and this term, okay, this is one of the viscous dissipation component, right. So, what this will give you is basically it will give you UK dy square, right. So, that means it does not depend on what is your gradient. It can be a positive gradient, negative gradient, whatever it is, like velocity can go up or down, whatever it is, it is the square of that particular quantity is always positive, right. So, the viscous dissipation term throughout this expression is always a positive number. Okay. So, that is what happens because of the square nature of this, and this you can show it for the other terms also, it is always a square. Okay. In terms of now, this is the expression that has been written in terms of the internal energy of the system, right. So, the internal energy of the system is Ek. In terms of enthalpy, and why we are writing in terms of enthalpy, there is a logic that you will find soon. In terms of enthalpy, if we write, enthalpy is nothing but this Ek plus P by rho k, right, this definition of enthalpy. You put the same definition over here, you basically have the same material derivative of enthalpy. Okay. In addition, you have a material derivative of pressure, rest of the terms do not seem to be get affected. Now, for a multi-component system, if we do a multi-component system like the one that we did in the last lecture, you can cast the same enthalpy in terms of the mass fractions and the individual specific enthalpies of each of the components. So, it is basically like a sum total. So, if the total mass is something like 1, omega k I is basically the mass of the ith component in the kth phase, okay, divided by the total mass. Okay. So, this is the mass fraction. Okay. So, mass fraction is multiplied by the specific enthalpy of that particular component, right. So, it will be just the summation. Okay. The left hand side will be just the summation of the each individual enthalpy components of each individual component, okay. The sum total of across all the components over there, right. So, that this q k double prime that you see over here, which we said as a conduction term, it is basically a little bit more complicated than that. If you look at this expression over here, the first term you recognize immediately, that is like the Fourier's law, right, that is the Fourier's law of heat conduction, correct. But you do not know much about the second and the third term, right. The second and the third term is basically the heat transfer due to interdiffusional convection, that is the first term over there, and also the heat transfer that due to the concentration effect. Okay. As you know that concentration can be transferred by temperature gradient. Similarly, heat can also be transferred by concentration gradient, but these are strictly, these two components are very strictly second order effects, and most of the cases they are negligible, right. Okay. But however, many of the equipments that we use actually work on the second order effects, right. One example of that is basically your thermoelectric, okay, thermoelectrics, that is a second order effect essentially. You also have like thermoelectrics like Peltier cooling and things like that, these are all second order effects. That also thermocouple, one of the most important things that you use, that is also a second order effect, right. So, you have actually second order effects in situations where they may be very important, but most of the time they are very negligible. We are only concerned with that first one, that is heat transferred due to the temperature gradient, not due to concentration gradient or any other thing. Okay. Now, if the kth phase is isotropic, what do we mean by isotropic? Means that there is no variation in thermal conductivity in any direction. So, there is no thermal conductivity is not like kx, ky, kz, right. They are all the same as k, right. But there can be materials which can have directionality, like for example, if you take a rod, you take a material which is composed of these rods like say nanorods or something like that. Okay. What will happen is that the conductivity along this direction and the conductivity along that direction is different. Okay. So, but in cases where the conductivity is the same across all the directions, okay, you can replace them by a single conductivity parameter, right. Okay. And these are once again the second order components that we talked about, and these are the terms that we already spent, viscous dissipation and the corresponding pressure. This is written in terms of enthalpy. Now, if we take a pure substance means I is equal to 1, right. There is no multi-component systems over here. So, the expression reduces to something like this, and we are neglecting this also, okay, which we can safely do because these are all second order effects as we talked about. So, this is basically the once again the same three terms that you are familiar with. Now, we can do a little bit of jugglery, right, because this is not a very usable form, okay, that is not the one that you normally encounter with. So, what we do is that this material derivative of the enthalpy of the kth phase, okay, we write it as the differential of Hk with respect to T at constant pressure into the corresponding material derivative of the temperature of the kth phase, right. Similarly, we do the same thing with respect to pressure at constant temperature, and we cast this Pk in terms of dt, right. So, what we have essentially taken is that it is a function of P and T Hk, right, which is a standard thermodynamic definition, right, that your property can be a function of, you can specify the property in terms of two other properties, right. Okay. Now, the thermodynamic relationship, this particular relationship is important, that is the change of the enthalpy of the kth phase with respect to temperature for a constant pressure is nothing but Cp, the specific heat at constant pressure, right. Okay. Similarly, the change in enthalpy with pressure at a constant temperature is given by this expression, where this beta k is nothing but the coefficient of thermal expansion, which is nothing but the change in density of the kth phase with respect to temperature at constant pressure. Okay. So, that is beta, that is the coefficient of thermal expansion, correct. So, we can write now the material derivative of the enthalpy in terms of two components, the Cpk, which is the specific heat at constant pressure for a particular phase, and we can write it in terms of the pressure and the corresponding coefficient of thermal expansion, right. Okay. So, not a problem. So, this entire equation therefore now becomes a much more good looking form, I should say. Okay. So, it is given in terms of temperature. Temperature is something that you can measure easily. So, this gives a little bit of a latitude to us. Okay. This pressure term and this pressure term can be combined together, right, because that 1 basically drops off, okay, that 1 minus beta k. So, you just get this nice looking expression and the rest of the terms remains the same. Now, for an ideal gas, if this is an ideal gas, okay, you can see that this particular expression now reduces to something like this from here to here. Now, for incompressible flow with constant density, okay, we know that the pressure term will actually vanish, that dpk by dt, that will vanish, right. So, you get this particular form. So, we are reducing it slowly, right. The viscous dissipation term, now if you write it in Cartesian coordinate, you can see what I talked to you earlier, it is always the square, right. So, it is always positive, always the square, right. Now, for incompressible flow, okay, the species conservation. So, this is the expression that you normally would get. Now, that k can be taken out also if it is like a constant thermal conductivity. So, this expression can become, is the material derivative of T, can be written as kk Tk plus qk triple prime plus the viscous dissipation term. Got it? Okay. So, now this is basically nothing but the Laplace of temperature of Tk, correct. This is the convective derivative once again. Heat generation term, in many cases it can be equal to 0, and then the viscous dissipation term in many cases can also be equal to 0, right. Okay. So, similarly, species conservation that we did in the last lecture, okay, in the integral form can also be reduced to something like this. We are not going through the details of the math once again. It exactly looks the same as the energy conservation equation. If in the energy conservation equation this and this becomes equal to 0, okay. So, this is nothing but the same as this expression that we have. Here of course, we have internal mass degeneration rate. If that can be also equal to 0, then you just have the species balance in its form like this. Exactly looks the same as the mass conservation equation, as the energy equation. So, there is still the material derivative of the mass fraction, there it is temperature, here it is mass fraction, another scalar, and this is basically nothing but the corresponding diffusive flux, okay, which looks very similar if you consider the next expression for a binary system. So, if the system composes of A and B, that is two components, one diffuses through the other, you can see that this is like rho k d omega k A. This is, I am writing it for the A component, that is the convective term. This particular term looks exactly the same like your diffusion term in the, it looks exactly like this. If you look at the similarity, you can see it. This looks exactly the same as this, right. Okay. This looks exactly the same. Okay. So, this looks very similar, this is also a diffusion term therefore, and this is the corresponding generation term. In many cases it can be equal to 0. This dAB can also be a constant. So, in that case this will come out and you will once again get a Laplace of the omega Ka. right. So, this Laplace of omega Ka is very similar to this particular Laplace of the temperature. Okay. So, this is what we have for compressible incompressible flow for constant density, right. So, we have done all the differential formulations over here. Okay. So, to say now we are going to move on to what we call the jump conditions. Okay. Why are the jump conditions important? Now, the phase equations that we introduced above, okay, can be only applied within each phase and up to the interface, right. So, it is sum total of each of the phases, right, that we did, we just summed over all the phases. However, they are not valid across the interface where sharp changes in various properties happens. Like we said, when water, liquid water gets converted to water vapor, there is a density change of approximately 1000. So, appropriate boundary conditions at the interface must be specified to solve the governing equations, right. Okay. So, the interface conditions will serve as boundary conditions for the transport equations in the adjacent phases, got it. So, you have to specify when you do the equations, this comes as like two phases, this comes as an interface, serves as a boundary condition. The jump conditions at the interface can be also obtained by applying the basic laws of thermodynamics, momentum, energy, that is energy is basically thermodynamics, conservation of mass, momentum, and the second law of thermodynamics at the interface. Okay. So, let us look at the situation for a conservation of mass over here. Okay. So, the integral formulation for conservation of mass for a control volume that includes two phases, okay, is already we have covered that. Now, what we are doing is that we are adding the interface term and we are subtracting the interface term. Okay. So, up to this part it was already there, right. If you just take this out, this and this was already there, right, except now that we have added the interface, right, and we have subtracted the corresponding interface over here, getting my point. Okay. So, what we have done, this is summed across all the phases. Okay. So, what we have done is that for each phase we have added the interface and we have taken the interface out. This is for two phases, got it. We have added and subtracted the two phases, the AI. AI is basically the interfacial area, right, whatever it may be, right. So, we have added the interfacial area here, we have subtracted the interfacial area there, that is what we have done. There is nothing illegal, you just have added and subtracted the same term, right. Now, let us look at this particular expression, this particular cartoon that we have over here. This is one phase, this is the other phase. It is very simple phases, looks like an egg. Okay. It is actually separated by this interface area which is AI, right. So, it is like a membrane which basically is separating the two halves. Okay. So, if you have seen the toys, okay, like you will have that, you know, a separation, clear separation between the two components. Okay. So, it can be a vessel, it can be anything. So, this is phase 1, this is phase 2. So, this is the area, this particular area is A2, that particular area is AI, right. So, V1 is bounded by AI and A1, correct. V1, if you look at V1, what does it, if you consider the whole V1 volume, it is surrounded by A1, it is also surrounded by this AI, right. So, if you consider the area, the area that actually encloses V1, you will find that it is AI and A1. Similar for V2, it is basically A2 and A2 and correspondingly AI, right. Okay. So, using divergence theorem and Leibniz rule like what we did last time, okay, we convert the corresponding as we know the area integral to the corresponding volume integral. So, this part is what has been converted to volume, this part is the interface. So, this part is the interface part, right, not the 0, but up to this part is the interface part, right. Now, we already know that this part has to be equal to 0, the kth phase, is not that so? We already know that this has to be equal to 0, right. This is summed over V k, nice and easy, right. So, we know that this part has to be equal to 0. Are we okay with that? Because this is nothing but the conservation of mass equation. For each individual sub volume we have written it. Okay. But however, this implies that this particular term, which is nothing but this written across that interfacial area A I, that must also be equal to 0, right. That must be also equal to 0, except that it is over A I. Okay. Now, since the integral is equal to 0, the integrand should be also equal to 0 because of the, because this area can be very small. Okay. So, what we have over here is that it is sum total, because it summed over both the phases, right. So, it is a sum total of phase 1 and phase 2, right. What it is? It is rho 1 into V 1 relative, that is the velocity with respect to phase 1, okay, and the velocity with respect to phase 2, right, and the corresponding surface normal in both the phases, right. Remember this here, of course, the surface normals are equal and opposite, because the phase is a nice flat interface, but it can be anything. It can be the same thing where the interface is something like that, right. So, this can be the interface also, does not really matter, okay. But whatever it is, this is given by that particular expression, right. Now, if the V reference velocity equals to the interface velocity, that is the reference velocity with which it moves the control volume, okay, if that is equal to the reference velocity, okay. So, the relative velocity therefore can be written as V 1 relative is basically written as V 1 minus V I, okay, V I. So, this is 1, this is I, there is a difference, okay, and similarly this is V 2 minus V I, right, it is the same thing, okay. Now, if you consider this particular term, what does this designate? This designates some kind of a mass flux, right, is V k minus V I into dot n k into rho k, it definitely designates a kind of a mass flux, right. So, it essentially means the sum total of the two mass fluxes considering both the phases has to be equal to 0. Okay. So, m 1 double prime, the m 2 double prime has to be equal to 0. Now, the thickness of the interface here has been considered to be 0. So, this is like a membrane, that is what we said, and if you can take a look at this, this is a typical interface, this is like n 1, this is n 2, okay, this is interface, this is region 2, this is region 1, this is the tangential directions. So, n 1 is basically the negative, one surface normal is the negative of the other, okay. So, naturally you can rewrite this equation, this equation can be rewritten in this particular form. If there is no phase change, that means the m 1 and m 2 are basically equal to 0, then you have the velocity V 1 is the same as V 2 is the same as V I, right. So, m 1 and m 2, now you can clearly see the link m 1 dot double prime and m 2 dot double prime is basically the transfer of mass, okay, between the two phases. That means there is a phase change that is going on. So, there may be liquid water here, vapor here, some liquid water is getting converted to vapor, or some vapor is getting converted to liquid water, whatever may be the case. So, the interface is a thin interface, the surface normals are basically equal and opposite to each other, okay, and this is the expression that we can write. If there is no phase change, that means this and this basically becomes equal or negative of each other, and we get the velocities to be the same as the interfacial velocity. Okay. So, the velocity in the two components is the same as the interfacial velocity, got it. However, if these are not the same, then of course, you have a net transfer of mass, then also this expression will be valid, got it. Okay. So, this is one of the key things that we can find out in this particular exercise. Okay. Now, we look at the momentum equation in the next one, but you can clearly see that by defining an interface, okay, what are the conditions across the interface. So, if there is a mass exchange, what will be the condition? If there is no mass exchange, then what will be the condition? And it is easy. What we have done is that we have basically added and subtracted in our integral formulation the AI, that is basically nothing but the interfacial area. We have added it to each of the phases, okay, and we have taken it out also, right. And then just by using the continuity expression, we have set this part to be equal to 0, and then we have worked with this particular part only, right. And that part is also equal to 0 because of the reason that the entire sum is equal to 0, and then we have cast, if there are two phases, we have cast it in this kind of a component, and we have taken the V reference velocity to be equal to the interfacial velocity in this particular case. So, you stop the lecture over here, okay. In the next lecture we will pick up the momentum, the corresponding momentum equation, and we will see what that implies, okay. Thank you.